Good afternoon, everyone, and welcome to the webinar. We'll be talking about maneuver processing in orbit determination today. As Meg said, please feel free to ask questions, and we've got a couple folks who are ready to try to answer them on the fly while we keep talking, and we'll have another opportunity at the end of the webinar to take more questions. Okay, so to kick things off with, I'd like to start out with our first poll question, just to get a sense for the environment that we're working in here and what it all looks like.
I will launch that on your screen right now.
All right, the first question is how many maneuvers a week does a new GeoBus typically perform? And by GeoBus, I'm talking about a newly launched GeoComSat. Okay, so there is no one correct answer to this question, but typically the newer buses have electric thrusters on them, and because the operators and manufacturers are taking advantage of the efficiencies that those electric thrusters provide. As such, they have to burn more frequently. So typically a new GEO satellite these days is maneuvering anywhere from 1 to 4 times a day. So the correct answer would be either 7, 14, or 28 times. We'll talk more about this later on in the webinar. But the point of that poll question really is to try to get across the point that maneuvers are much more frequent than ever before. When I first started doing satellite operations more than 25 years ago, spacecraft we used to operate typically did an east-west station keeping maneuver once every 4 weeks and a north-south once every 90 days. The technology has changed since then, and it makes the orbit determination process much more interesting, and being able to work around maneuvers now is a little bit more challenging. So maneuvers fall into really 2 types, and this is I say this from the standpoint of somebody has to deal with both cooperative maneuvers, which is I have all the information about the maneuver. I'm the operator. I plan the maneuver. I know the start time, the stop time, the duration, the thrust levels, everything I need to know because it's my spacecraft. And so when I execute a cooperative maneuver and I'm trying to then do orbit determination, I'm interested in understanding and calibrating the maneuver performance. And then there's the uncooperative maneuvers. This is typically done by somebody who's trying to do orbit determination on a spacecraft that isn't theirs. This is typically something you run into when doing space situational awareness type orbit determination, where you're tracking something with measurements that don't involve the satellite itself. So we're not doing owner-operator ranging, but we might be doing radar ranging, tracking with the telescope, that type of a thing. In an uncooperative maneuver, you have no a priori information. Matter of fact, you may not even know that a maneuver has occurred or not. And so that makes the OD process a little more challenging, and we'll talk about that. In some cases, you can constrain the maneuver and take advantage of that information. And we'll see some of that later today. So orbit determination is fundamental to effective space situational awareness. It's sort of one of the driving elements in understanding what's up there and what's happening, where it's all at. And our experience in looking at these types of problems has shown that the use of a Kalman filter estimator offers a number of significant advantages. It allows for faster maneuver detection, characterization, and recovery during the OD process. The OD also serves as a tip-off regarding maneuver detection, and is really important for performing the maneuver recovery and characterization process. We'll see some examples of that. So as we have dealt with these problems and trying to solve them, and we've tried to do a couple different things. There's a couple things that we found have been very helpful. The ability to process multiple satellites simultaneously. So when you're doing orbit determination, typically it's done on a per satellite basis, but there's no reason it has to be that way. And when you have shared common tracking resources or other shared items in your state space, processing multiple satellites simultaneously can really pay off, particularly when doing proximity operations or other closely spaced objects. The ability to process relative measurements, what we call the closely spaced object problem. In some cases, spacecraft themselves have tracking payloads on them. And if you're trying to do rendezvous or prox ops or just kind of keep an eye on your local neighborhood, the ability to process the relative measurements is very useful. Having a full realistic covariance is critical to downstream decision making. Every estimator is going to produce a covariance. The question is whether you actually believe it or not. And so having the proper uncertainty models, not just in your measurements, but also in your forces that are acting on your spacecraft, is really important to having a downstream realistic covariance. Once you have that covariance, you can then use that to make decisions in terms of how it affects your course of operations and course of action and the other tracking type decisions that you want to make. The ability to fuse measurements of all kinds in a single OD process. Depending on what community you come from, certain measurements are more common than others. If you're an owner-operator, typically you've got ASL range, maybe you have some Doppler. If you come from the SSA community, you might have a RA deck from a telescope, you might have a radar. But then there's additional measurements that sometimes start to come into play: time difference of arrival, frequency difference of arrival. And what you really want to be able to do is bring all this data together in one common OD problem and take advantage of everything. Every measurement, no matter how poor the actual tracker accuracy may be, every measurement can bring something to the table, and you want to take advantage of that. And then it's convenient to treat everything as constant because it makes the math easy. Unfortunately, that's not the real world, and so we have a lot of time-varying processes that are going on in the middle of the OD problem. Your measurement biases can change over time. Typically, we see this as thermal cycles throughout the day. We have hardware being unplugged or changed or reconfigured, causing step functions in our biases. Your force models acting on your spacecraft are not constant. So your solar panel area is, or your total spacecraft area is changing as your solar panels rotate. That affects your solar radiation pressure profile. It affects your drag profile. Even your thrusters and thrust directions and orientation can be changing. So all these things mean you need to be able to treat these as time-varying processes and estimate that as you go throughout the orbit determination. Another key thing is as you start to deal with maneuvers now, classically speaking, if you looked at it using like a typical batch least squares, you would do an OD fit up until the time of the maneuver. Then you would stop your fit, collect more tracking data post-maneuver, and do a post-maneuver fit. That process works fine if you have enough time to do that. But as we start looking at having maneuvers 4 times a day, you no longer have the option to have a maneuver-free period to get a nice clean fit. And what you want to be able to do instead is do the OD through your finite maneuver and take advantage of the information before the maneuver, through the maneuver, and after the maneuver. So you don't want to have to break your OD process and start and stop it. You want a continuous process. So now we're going to start talking about the maneuver processing part. So we're going to break it up into, in the context of uncooperative maneuvers, the detection, characterization, and recovery part of the process. And how fast you can do this is a critical piece for effective SSA. Everybody wants to know, what's my maneuver look like right now, or what's the other person's maneuver doing right now. What it did 5 days ago is not as relevant when you're in the middle of an SSA problem. Without timely detection, recovery, and characterization, you may not have time to do your downstream products that depend on that. Could be something as simple as the conjunction analysis, or trying to make a decision about whether the spacecraft is doing something that could be potentially threatening or hostile. So the first step in that is maneuver detection. And when you're trying to do maneuver detection, you're trying to figure out, is the spacecraft maneuvering? Because that might be a tip-off, as the type of activity the spacecraft is starting to do. That could be rendezvous operations, or just simply aligning the orbital plane prior to a potential rendezvous that could be weeks or months later. Or is it initiating proximity operations? So set the stage for this. It's important to understand there's a couple different ways you might want to model a maneuver. And inside of ODTK, we offer two options. There's the instantaneous or impulsive maneuver, or you can do a finite maneuver. The instantaneous maneuver is the classic maneuver you learn in your first course in astrodynamics. It's simply an impulsive delta V. It's a great modeling choice if you have a very short maneuver, especially if there's no tracking data during the maneuver. It's very easy to calibrate. We'll talk about that. But the instantaneous maneuver model starts to break down as you start to get longer and longer duration maneuvers. It's no longer appropriate. And that could be because your coordinate frame that you're doing the maneuver in is actually rotating with your trajectory. Like, for instance, if you burn in an RIC frame, the longer that maneuver is, the more your actual trajectory frame is rotating during the course of the burn. Of course, a finite maneuver can be a little bit harder to calibrate because it can be time dynamic in both the magnitude and the pointing. It introduces intraditional solve for states into your state space. On the other hand, it gives you great flexibility, and we'll talk about some of the ways you can take advantage of that. So if you're going to use an impulsive maneuver, it's very simple. You specify the epoch and the delta V components, and that we've now got the magnitude, the direction, and the time, everything we need. But you do need to be conscious of the fact that depending on the type of tracking data that you have, you need to know that you may be lying to the filter. There's an implicit mismatch between the impulsive assumption and reality. All maneuvers at some level are finite. They may be short, but nonetheless finite. And so if we have a true finite maneuver covering this time period, and we have tracking data that's showing up quite frequently, we've lied to the system because we've said the maneuver is only occurring at this time t epoch, but in reality, it's covering this entire period here. And what we can end up with is a situation like this, where there are measurements that are occurring during the actual maneuver, but your estimator doesn't know. And so what happens is the lie is exposed because when this measurement right here occurs, the maneuver is already in progress in reality, but the estimator hasn't applied the delta V until it gets to this point. And then it applies all the delta V. In the meantime, the maneuver still really isn't complete yet, and this next measurement comes in. And this is a sort of the known lie. And so what we want to make sure is that we notify your estimator of that. And so we can do that by specifying two additional parameters with our maneuver, essentially the time before after start and the time before end. Essentially, where is my epoch relative to the actual maneuver itself? What this allows the estimator to do is essentially ignore the measurements that fall in this window so that we don't try to process data during the middle of the essentially the effective lie. This nonetheless is a great technique for modeling short duration maneuvers, and this is a situation you typically might run into if you're flying a spacecraft with a GPS receiver where we have very frequent measurements, every 1 second or every 10 seconds or something like that. How do you calibrate an instantaneous maneuver? It's really quite easy. In ODTK, what you would do is you would run the filter forward in time, you run the smoother backwards in time, and the smoother can take advantage of the fact that it knows this is an impulsive maneuver. Because it's impulsive, we know that the position after the maneuver must be the same as the position before the maneuver. And since the smoother has information to the left and the right of any point in time during the estimation process, it can enforce this position criteria. And then it knows that the velocity after the maneuver is equal to the velocity before the maneuver plus a delta V. And essentially the smoother can now solve for the delta V directly. And that's exposed in the instantaneous maneuver summary report. So impulsive maneuver is very useful, very handy because it makes the calibration process very easy. We can observe the delta V directly. And we can do this even when we don't have tracking data during the maneuver because the smoother has folded information backwards across the maneuver itself. If we want to use a finite maneuver model, then we have to specify the burn start time, the burn stop time, and thrust levels, direction, what frame the maneuver will be occurring in, because sometimes your frame may be rotating because your spacecraft attitude is rotating. And so when we do all this, we're actually adding magnitude and direction states into our estimator state space. And you can specify the uncertainty in each of these. So you can start to bound what we think the nominal performance is going to be. And we treat these as Gauss-Markov processes. They're a stochastic model. They're allowed to be time varying based on the half-life and the uncertainty that you as the operator specify. And during the maneuver calibration process, these are typically parameters that you're trying to fine-tune as you start to observe these maneuvers over and over again using the same thruster sets and stuff. You can share common states across maneuvers if you find that you're performing the same maneuvers over and over again using the same thruster configurations. So for instance, if you're doing a cross-track maneuver twice a day with electric thrusters, you may essentially have a north set and a south set. It's advantageous to say, I'm going to establish a north set of thruster states, a south set of thruster states, and reuse them with each maneuver. It helps manage the state space and share and fold information from one maneuver into the next. Finite maneuvers are also a useful tool for modeling unknown accelerations. You can put in a very long duration finite maneuver and it will soak up unmodeled accelerations that are going on in your system. It's sometimes useful for recovering strange slow radiation pressure or drag mismodeling. Of course, the flip side, with great power comes great responsibility, and putting in arbitrary finite maneuvers to soak up unmodeled acceleration problems is a great way to hide a lot of things, and it's easily abused. So it's not a first step to go to, but it is a tool in your arsenal. To calibrate a finite maneuver, you typically, again, run the filter and smoother across the maneuver, and then you can start to pull out your states that you've been estimating off the smoother. So you can graph the maneuver state corrections in a particular frame of choice, like for instance in inertial corrections or the RIC corrections, examine how they change over time, and then also look at the filter smoother consistency test results on the maneuver states. And we'll talk about the filter smoother consistency test here in a few charts. And that way you can start to observe the overall trend in the thrust profile, because sometimes, depending on the nature of your thruster, you may find that there are ramp ups or ramp downs in the maneuver process. Another thing that's important to sort of understand is how your tracking strategy affects your maneuver observability. So in this case, we've got a cartoon here of an Intrack maneuver. So imagine we have a nominal orbit that's roughly circular and it looks like this, and we're planning an Intrack maneuver that's of this magnitude. But in reality, we got a little bit more. We got a little bit of extra delta V. So instead of being on this middle ellipse, we're actually on this actual ellipse orbit. And if you look at this diagram, it starts to become quickly apparent that with the additional delta V, you're starting to get more and more separation between your expected orbit and your actual orbit. And that, in the case of a Intrack maneuver, that position error continues to grow because essentially we've changed the semi-major axis. We have a different period now. And so the overall position error is going to continue to grow and grow and grow over time. So as we look at where to take tracking data and in order to best help us understand that we've got a additional delta V error in our maneuver, ideally, the longer I wait to collect the tracking data, the more observability I have because the position error has grown. Of course, I don't want to wait forever. I really would like to know this as soon as I can. So in general, you want to start tracking as soon as possible and continue it as long as you can. The longer you go, the more observability you're going to get. Of course, the observability is also a function of how accurate your measurements are and what type of measurement you have. Is it a range measurement or is it angles? How good are your angles? That kind of a thing. For cross-track maneuvers, you have a similar type of a setup. In this case, what we plan to have here is a side view of the orbit plane. So let's imagine that we were on this original flat plane here, and we're going to do a maneuver as we go through the nodal crossing. And we're trying to get to this new inclined plane. And I've greatly exaggerated the size of the inclination change. But in reality, we got a little bit extra delta V. And so instead of being on this middle plane, we're on this top plane here. So this error in the orbital planes is most visible when we're at this point in this orbit, or conversely over on this side of the orbit. If you look at that from a top-down perspective, which is what we have on the other side of the diagram here, my original orbit was this flat circle because I'm looking straight down on the system. I was trying to tilt it a little bit and end up on this slightly tilted view of this middle ellipse. But in reality, I've tilted it even more, and I've got this inner ellipse. It only looks elliptical because I'm essentially projecting the circle, a tilted circle here. We didn't actually change the eccentricity. And so again, my maximum position error is most visible here and here, which is essentially 90 degrees and 270 degrees away from my line of relative nodes. So if I'm trying to develop a tracking strategy to pick up cross-track maneuver errors, I want to be looking somewhere over in this part of my orbit, about a quarter rev or 3/4 of a rev or pure orbit period after my maneuver. Doesn't mean it's not observable prior to that. It's just it's a strategy to look at. So with that, let's introduce our second poll question. Okay, so what type of maneuvers are you concerned about? Cooperative, uncooperative, both? This is pretty much driven by the community in the problem areas that you look at. If you're an owner-operator, you're typically looking at cooperative. And if you're more interested in SSA or what's going on in general up there, you might be interested in uncooperative. All right, so it looks like we've got about 25% cooperative, 30% uncooperative, and about 45% both. So it's pretty much about what we expected. So very interesting. A lot more people are interested in uncooperative maneuvers these days. So given that we've got interest in uncooperative maneuvers, let's talk about maneuver detection. So as I'm trying to do an orbit determination on an uncooperative object, I really know nothing about it other than that I can track it. We have to decide when do I think a maneuver is occurring? How do I detect that? What are some of the things that the pitfalls or the things that are going to potentially compromise my decision making there? And there's things that can really mess you up. There's no perfect answer here, but there are a bunch of best practices that have been developed over the years by the people that sort of live this problem. And you want to make sure that you've got the proper tools and flexibility to slice and dice this a couple different ways. So here's a typical graph. This is what we call a residual ratio graph. The measurement residuals are the errors between your actual measurements and your projected measurements based on where you thought the object was going to be. The residual ratio is those measurement residuals that have been normalized by the uncertainty. What this allows us to do is mix measurements from different trackers with different measurement types and measurement accuracies. By putting them in this normalized space, it allows us to look at it all in aggregate. So what we're expecting to see here is that our residual ratios should be within plus or minus 3 sigma, which is why you see these lines at plus or minus 3. So here we can see we've got a pass of data here, we've got some here, we've got some here. And you notice that most of this data is in plus or minus 3 sigma, but we do have a couple of outliers up here. Now, when we have a maneuver that occurs, as we discussed earlier, the orbits are going to be a little bit different than what you expected. So your measurement residuals are going to be different. So the question is, are these measurement residual ratios telling us there's a maneuver going on or not? Now, in this case, as an experienced analyst, when I look at this, I would say there is no maneuver here. A couple things that are leading me to that is I've got good data prior to this bad data, and then I've got good passes afterwards. Had it been a real maneuver, it's likely, although not guaranteed, that these downstream passes would also start to show outliers. In this case, they don't. And I can tell by the color coding, in this case I've color coded based on the measurement type, that one measurement type is still in bounds and the other one is not in bounds. So it's not every measurement from that sensor is out of spec. So in general, I would say this is not a maneuver. Of course, more downstream measurements might shed more light on that. And this is more likely a problem with the sensor. Either the sensor itself is having issues, or it just could simply be that its tracking data is mistagged. Mistagging is a huge issue in doing SSA problems. And when we have mistagged data being fed into a maneuver detection process, it can make it look like there was a maneuver. In reality, everything was just fine. Here's another example. In this case, again, we've got our residual ratios. We're within plus or minus 3 sigma at the early stages here. We got a little bit of a tracking gap. And then we can see that we're starting to get some stuff out of bounds again. And what we're seeing is multiple passes are showing out of bounds data, multiple sensor types, different sensors. And this is really a tip-off to me that this is potentially a maneuver, because I've got too many things that would have to be going wrong simultaneously for it to not be something on the spacecraft itself. So this is worthy of investigation, and we would start our maneuver process. So this is sort of the basics of starting to do maneuver detection. So as we think there's a maneuver going on, we also have to decide, as I start to adjust maneuver models and such, when am I done recovering from the maneuver? So I have to detect that the maneuver has stopped. I have to then try to figure out how much more tracking data do I need to process to essentially recover my orbit solution. So we want to understand, when is it done? How do I characterize my maneuver? Again, there's no perfect answer, but there's a couple things we can look at. So for detection, we need to detect that the maneuver has occurred. Then we need to do an initial characterization of the maneuver with whatever data that we have, which may not be much. Okay, but the point of the initial characterization is that we need to get some sort of an initial solution going so that we can continue to maintain track custody of the object. Because if I can't continue to track it, there may not be any more downstream tracking data that may get lost. The spacecraft may go lost, or at a minimum, that the observations may become uncorrelated. So we need to start characterizing the maneuver as soon as we can, and start putting together an initial assessment of the orbit in the maneuver, so that we can continue to point our post-maneuver sensors. As tracking data continues to flow in, we're going to continue to characterize and refine the maneuver hypothesis. What that's going to do for us is give us more insight into, well, what was the size, direction, and timing of the maneuver, and it's going to collapse the uncertainty on our orbit estimate. And we'll continue to run this process, folding in more and more tracking data as each pass becomes available, until our post-maneuver covariance is reduced to acceptable levels. Now, acceptable has a variety of definitions, but in general, a rule of thumb is to get back to your pre-maneuver covariance. If it was a really large maneuver, say a GTO that was then circularizing in a GEO, you won't get back to your pre-maneuver covariance because you're in a completely different orbit, but you'll get back to a stable covariance. At that point, we can declare victory, and we can watch for our next maneuver. Of course, it may be that a second maneuver has occurred while you're still recovering from the current maneuver, and you have to be able to identify that, finalize essentially the first maneuver as best you can, and then continue with starting the maneuver process for the second maneuver. So as we're running our estimators, what we prefer is a filter smoother solution, and what that's doing for us is a couple of things. As our filter is processing, moving forward in time and processing tracking data, our state estimate, which includes our orbit and a variety of other parameters, sensor biases and such, our state estimate xk at time tk reflects all the tracking data that the filter has seen up to this point. However, as I continue to move along forward in time, I can eventually get to the point time TL here, where I can now run backwards in time. And if I run the smoother backwards in time, and I get to that same time tk, the smoother can take advantage of the fact that it knows about tracking data from the left side, it knows about tracking data from the right side. And because it has more information, it can produce a better answer. That more information directly leads to a smaller covariance and an improved answer. And we take advantage of this now to help us figure out what's going on, say, at time tk, where there might have been a maneuver. The smoother also allows us to calculate what we call is the filter smoother consistency test. This is a really powerful test statistic that can be applied to any parameter in your state space. And the way it works is this. I can take any parameter x from and take the estimate from my filter, difference it with the estimate from the smoother, and that difference should have an uncertainty that looks like this denominator term, the sigma of that parameter from the filter minus the sigma from that parameter from the smoother, and then you square them, difference them, and square root it. The net result is that you end up with a test statistic that should be within plus or minus 3. And this been shown that this is a necessary condition for having a realistic covariance. By calculating this test statistic, typically on the position states, the velocity states, we can identify if we've got a modeling problem, and then update our assumptions and processes to try to correct that modeling. So the value of this, because it's a necessary condition for having a realistic covariance, failing this test means that you've lied to the filter in some manner. There's some typical classic lies. Your force model is too simplistic. You don't have a good enough geopotential or a good enough SRP model or something else. Your measurement white noise sigmas are too tight. That's typically a sensor calibration problem. Your measurement biases have errors that are too large. You've mismodeled the solar radiation pressure or ballistic coefficient. Or in the context of this discussion today, you've mismodeled a maneuver. You told it looked like X, and in reality it was Y. Or you haven't modeled the maneuver at all, which is essentially a force modeling error. But we can look at this test, the filter smoother test, to really give us some clues as to what's going on. So let's take a look at some examples of that. This is a graph of the residual ratios of a simulated GEO performing a normal station keeping maneuver. And the measurements that we're processing in this case were time difference of arrival measurements. And the scale is greatly exaggerated here, so my plus or minus 3 sigma lines are really squashed. But you can see there are some measurements being accepted in here. And then what you can see is that something has occurred somewhere between this last good set of data, and then we've got data that's clearly well outside the ±3 residual ratio bounds that I'm expecting. Then it goes out of bounds, and it comes back down, and keeps going. Okay, so this is a typical tip-off that I have some sort of a delta V going on. Now, obviously, I would normally wait many hours like this. I'd be looking at the first couple of data points and starting to get concerned. So if I have no maneuver modeled in my estimation process, but there really was one, you can end up with a residual signature that looks something like this. Now, if I model the maneuver correctly, as indicated by this blue bar in here, and this is a typical way we mark finite maneuvers in ODTK, if everything's modeled correctly, then I should be within ±3 sigma in my residual ratios, and I can see that both before the maneuver and after the maneuver. And if I calculate that consistency, filters through the consistency test for all 3 position states and all 3 velocity states, in this case we're doing it in the RIC frame, I can see that my test statistics well within ±3 sigma before and after the maneuver. And in this case, what I've done is I've done the orbit estimation directly across the maneuver. The maneuver model is great, and I don't see any issues whatsoever with these results. But now what we're going to do is we're going to perturb that and assume that we maybe didn't do such a good job. So in this case, what if I actually shift the burn center by 10 minutes? Remember, this is a geo, so a 10-minute burn center error is not that huge. Now, if I look at the residual ratios, you can see that I was good going into the burn. I lied to the estimator. I told the burn it was 10 minutes early. I've got a burn error. And I can see that I've got some residual ratios that are okay after the maneuver, but some are still a little bit out of bounds. And if I look at the position and velocity consistency tests, you can really see they're blowing up. They're well outside ±3 sigma, and the timing of when it blows up is giving an indicator to me as to what potentially I have mismodeled, in this case the maneuver itself. You can really see it in the velocity here. So, and then also the fact that it happens to be the Crosstrack line suggests to me that probably I've mismodeled the Crosstrack maneuver. All right, so this is a powerful test statistic. It's telling me, I've got potentially an error here, but of course I can usually see that even in the residuals here. What happens if I only perturb the burn center error by 30 seconds? If I only looked at the residual ratio space, I might think this is a perfectly good maneuver model. And it's not horrible, but we can do better. And what's telling me that we can do better is that the consistency tests are still blowing up. Now, position is just barely going out of bounds, but velocity is really telling me that something's going on here. So again, we've got a mismodeled maneuver, and by examining these test statistics, it gives me a clue as to the fact that I might need to tweak my my maneuver model to get a better fit. Turns out the answer is about 50% of spacecraft that are active in GEO today have electric thrusters. Most have a mix of electric and hydrazine, and some of the newer ones are all electric. So the challenge of dealing with maneuvers that are frequent is happening more and more as these spacecraft are maneuvering more and more. So if we talked about cooperative maneuvers and how you might calibrate them. You put the maneuver model in, you fly across it, you evaluate the calibration results. If you're dealing with uncooperative maneuvers, you have to start, when you start to detect a maneuver, you have to go through and start to try to figure out what's going on. You start injecting different maneuver hypotheses. Is this an Intrack? Is this a Crosstrack? Is it a Crosstrack radial? Sometimes they have the canted thrusters. And then you start evaluating your residual ratios and your consistency tests, trying to figure out what's the best fit maneuver to apply here. As we went through this process and started doing this, we realized that we don't want to do that by hand, and so we built a tool to help with that called the Maneuver Processing Tool, or MPT. MPT is an additional application that essentially attaches to ODTK and takes control of it to help automate the characterization and recovery from maneuvers. And we're going to see more on that here in a minute. But for non-cooperative maneuvers, MPT runs a multi-hypothesis formulation in order to come up with the best initial guess, and then we refine that to try to achieve the best possible fit for the maneuver and orbit determination process. For spacecraft that are maneuvering really frequently, say 4 times a day, and maybe you don't have very dense measurement data because it's an SSA situation, you're not staring at the spacecraft the entire time. Then you have to decide if you have enough data, you can actually reverse engineer each of the maneuvers. If you don't have enough data, then you have to essentially smear across the maneuvers, and we can do that by adding additional unmodeled acceleration process noise. This is a very reasonable technique for doing this. The downside of it, of course, is that you're inflating the covariance more than you would normally have done had you been able to get higher quality tracking data and reverse engineer the maneuvers. This is typically a situation you might end up with electric thrusters. So typically what we might do, and if we have a spacecraft doing electric thrust multiple times a day, say for Crosstrack or inclination control, you might add just enough process noise to smooth out the Crosstrack thrust and yet still maintain visibility and sensitivity to an Intrack maneuver. Okay, so let's take a look at what MPT does and how it works. So I've got a video here. We've actually got that running. In this case, I've got a scenario in ODTK, and then we're doing a geo, and we're tracking it with a couple of TDOA trackers. And we've got a maneuver that has occurred. We can see our residual ratios looked good up until a time when they stopped looking good and blew up. Now this is fairly dense tracking data, but it helps really to indicate the problem. We see it in both TDOA and FDOA measurements, frequency difference of arrival. And we can see our consistency tests are blowing up as we look at the position and the velocity consistency. So all indications here are that something interesting is going on, and we want to try to deal with that. So what we're going to do is we're going to start up our MPT maneuver processing tool, and it's essentially going to attach to ODTK and start taking control of it. We've got a couple different hypotheses in here that we're going to run: a single burn Crosstrack, a single burn Intrack, a dual burn Crosstrack, and a dual burn Intrack. By dual burn, it means typically they're a half rev apart, and we can actually estimate both of them simultaneously, even if we don't have tracking data. This is a common scenario, for instance, if you're doing optical trackers or something like that, where one of the maneuvers may not be visible because it's daytime. So what MPT is doing now is it's actually running through each of the hypotheses in order to evaluate, essentially try to do an initial pattern match on what hypothesis looks good. And as it's running the scans, what it's doing is it's trying to generate simulated tracking data and see how the simulated data with a particular hypothesis correlates with the observed data that we have. This entire process, by the way, that we're running here with MPT is actually some patented AGI technology that we've been refining over the last several years. So as we go through postulating our Crosstrack, and you can actually see ODTK flickering in the background as it's processing it, it's gone through and it's come up with some first guesses. It's refining the first guess, and then it's going to tell us essentially a score and an objective function to tell us how well that first guess fits. The objective function is a combination of several parameters: the residual ratios, the position consistency results, the velocity consistency results, and how many measurements are actually being rejected completely. And what we can see now is our null maneuver hypothesis score, our objective function, was 827, which is quite high, indicating that's a bad hypothesis. Yet our Crosstrack hypothesis, our first guess, is at 2354, lasting for 180 minutes, and for a delta V of about 1 meter per second, and it has a very nice low objective function. So this is looking good. Because this looks like a good first guess, we're going to pass it on to our refinement process. And what we're doing now is we're running an optimization routine to optimize on both the start time and duration of the maneuver and try to bring that objective function down just a little bit more. So while that's running, I'll talk about these other hypotheses for a minute. The other hypotheses, had we not come up with a good Crosstrack score, we would have fallen down into evaluating the other hypotheses as well. In this case, we've got a very good Crosstrack score of 4.8. So you can see the duration was now 169 minutes. And for, again, total delta V is still about 1 meter per second. So we shifted the duration and the start time a little bit. We can apply that solution to our ODTK scenario and run our filter and smoother and see how the results look. So we'll take a look at our TDOA residual ratios. Again, they look well within plus or minus 3 sigma, and we can see our finite maneuver there. Take a look at our FDOA residual ratios, also well within spec. Things are looking good. We'll look at our estimate of the maneuver. We can see this is primarily a cross-track maneuver at a thrust level of about 0.095 newtons. And we can take a look at the impact on our position uncertainty. As we flew across the maneuver, you can see our position uncertainty increased because we've got thrust going on. And then as we get tracking data after the maneuver, it starts to collapse. And we can look at the velocity uncertainty, and a similar thing. It increases during the maneuver, and then as we continue to get tracking data, we're driving the uncertainty back down to try to recover the maneuver. You can see we've recovered in about 4 hours or so. Look at the overall impact on the smoother position uncertainty. You can see that we've essentially flown directly across that maneuver with really no impact at all. So that's an example of a very simple uncooperative maneuver recovery. We can also do, again, cross-track radial hypotheses, canted thrusters, radial only, a variety of different options in there. The analysts can actually build their own maneuver hypotheses and fly them. And then there's the ever popular recovery maneuver, which means we don't think it did any of those. So we're going to look for a maneuver in any direction and fly that. This, as I said, we've been developing this algorithm now for several years, and we actually run this at scale inside of our ComSpoc. And this is an example dump of that, where we're running this for all the spacecraft that are in orbit and characterizing maneuvers as we come across them. And again, it runs at scale, and we use it operationally every single day. The net result of when you start doing that and start processing and looking at particular spacecraft over and over again is that you can start to establish patterns of life. And so this is an example where we take the OD process, and we've actually generated a residual ratio graph here showing both optical tracking, TDOA tracking, and you can see we've got some maneuvers marked here. And we took all the maneuver times that we've been collecting, and we can actually start to build what we call the maneuver wheel. I'll show a zoomed in view of that, where we can start to characterize this particular spacecraft happens to do a cross-track maneuver every Tuesday, pretty much like clockwork. Each ring is a week worth of data. And you can see that the Intrack maneuvers tend to occur either on Thursday or Friday. And so as you start to do the maneuver reconstruction and recovery, you see these patterns of life, and that allows you to start making predictive analysis as to when their next maneuver should be. And that's very interesting. Of course, if it doesn't occur as planned, it makes you wonder what's going on. So with that, we've sort of done a really crash course of maneuver processing, some of the challenges involved in it, and both in a cooperative sense and uncooperative sense, and we'd be happy to take any questions.
Great. We have a few questions. Our first one is, how does this correspond to maneuver detection and air target tracking? Is this just measurement model, or does this include a process model noise?
It does include process model noise. So we're modeling the fact that we don't think the maneuvers are perfect. So there's uncertainty in the maneuver direction and the magnitude. And that shows up in the resulting orbit covariance and maneuver covariances as well.
Great. Next question. Will we cover, or can you at least cover a little on calibration of thrusters on orbit using tracking data?
Sure. So in a cooperative maneuver, typically what we're doing is we put in the plan to maneuver, duration, delta V, direction, etc. And then we run the filter across it, run the smoother. And then there's different reports and graphs you can generate in ODTK where we would look at the corrections to the direction and the corrections to the magnitude, or the magnitude of the maneuver. And then from that we can derive and find out, for instance, this particular maneuver might have been 98% of what we planned. We had a 2% shortfall. And then we can then fold that into our next maneuver process.
Awesome. The next question is, we are getting a couple of questions, or we actually are getting multiple questions about the Kalman filter we are using. Can you cover a little bit about that?
Sure. So the call it a Kalman filter is a bit of a misnomer. So the best way to describe it is it's an optimal sequential filter, where the difference comes into play is it's like an EKF, where we're doing as we process each of the measurements and do a measurement update to the state and covariance. Where the magic occurs is actually in the process noise model. So classically, an EKF would assume that the process noise is white, and it turns out in the orbit determination process that's definitely not the case. So what we have is customized process noise models for each of the forces. There's gravity uncertainty, density uncertainty, ballistic coefficient uncertainty, SRP uncertainty, et cetera. And so the analyst gets to specify the uncertainties and the half-lives and the stochastic models that drive each of those parameters. And the analyst gets to do it in a manner that's consistent with sort of the physics. So you're not trying to come up with a magic Q matrix to handle the model of process noise. The analyst is actually saying, I think I know my solar radiation pressure area is 40 meters squared with an uncertainty of 10%. And I think it's going to change over the course of 12 hours. And so by working in sort of a physical parameter space, we can then integrate that into acceleration space and down into velocity and position. So we call it an EKF because that's what people commonly know, but it's really an EKF with a customized process noise model.
Great. A few more. So you mentioned white noise. Can you add colored noise?
So for the measurements themselves, so if I'm doing simulation work, for instance, the measurements are typically done as white noise, but you can have the biases and such be varying over time. Of course, you can always feed in your own measurements. For the uncertainties on the maneuvers and everything else, we treat them as a Gauss-Markov process. So it's a correlated, exponentially time varying process.
Great. Can you address what kind of objects ODTK can support?
Sure. So currently we use ODTK in the context of our ComSpoc, where we're trying to do commercial space operations or tracking of everything. So we've done the entire public space catalog using ODTK. It's 20-some thousand objects. We do Earth-centered OD. We've flown operational missions around doing moon-centered OD. We can do heliocentric ODs, and we've done tracking ODs on the Messenger mission that was going to Mercury, and we're getting ready to support some Mars missions as well. So really, it's everything Earth-centered and deep space.
Great. We'll do two more. Can you comment on your experience with performing cooperative maneuver calibration with a batch filter?
Sure. So with a batch, typically what you're going to do is you can do like I said, typically you do a pre-maneuver fit and you can do a post-maneuver fit, and then you can try to say, well, I'm going to solve for my state before and after, and look at the change in my orbit, and then use that to sort of back out the thrust profile and the maneuver correction, and say, well, it was 10% hot or cold or whatever it might be. Now you can try to a more advanced batch tool might have the ability to model the maneuver, and then you can try to do a batch fit across maneuver. For instance, you can do that in ODTK as well. But actually solving for the maneuver parameters, typically the batch is going to assume that the maneuver is constant in magnitude and direction, and that's not necessarily the case.
Awesome. Last question. In your example, the tracking data was fairly dense. What would have happened to the maneuver estimation if the tracking data had been sparser, particularly across the maneuver?
Sure. So in practice, when we're doing SSA problems, we almost never have tracking data during the maneuver. It's not uncommon. For instance, you might have multiple revs without tracking data at all. And that really doesn't affect the maneuver reconstruction process much. Obviously, it's delayed because you have to get post-maneuver tracking data. So that delay is not ideal, but it's reality. And so typically we've gone 10 revs without tracking data because it was a large maneuver. And and nonetheless, the MPT is really quite robust to this situation. So what you might see is, for instance, if it looks like it was a cross-track maneuver and you went 10 revs without data, you may find that there are now potentially 2 times a rev, where the orbits were coplanar, times 10, there might be 20, potential likely maneuver times. And NPT will start to flag that. But what you'll find is that the objective function scores on each of those will not be the same. And there will definitely be some favored maneuver times. And then as more tracking data comes in, those will continue to be resolved. So we deal with the sparse tracking data problem all the time. It works really quite well. And that's the reality when you're doing the entire catalog.
Awesome. Thank you so much, Tom. And thanks to Nick for helping answer the questions. For those questions we didn't get to, we will be answering those individually after we sign off. Thank you all for joining and listening in. Make sure to sign up for our next webinar on January 9th on automated satellite threat vulnerability analysis. See you next time.